Hi everyone. In this video, we are going to do a quick review of how to draw a Lewis structure. Most of this is a review from Intro Chem or from Advanced Chem, but then there's a couple new little things at the end for looking at the validity of Lewis structures. So remember that when we talked about Lewis structures in Intro Chem, we said that this is a good way for determining how atoms are connected together in covalent compounds, and what we did was we did what we call the connect the dots method. So we looked at nitrogen, like an NH3, for example, for ammonia. When we look at nitrogen, because of its position on the periodic table, has 5 valence electrons, right? So 1, 2, so we draw 5 dots, each dot representing a valence electron, right? So, and then hydrogen has 1, and so we draw our atoms in, and then we kind of play the connect the dots game, where we form a bond here, and here, every time we have an unpaired electron, we can form a bond, and we end up with a structure that looks like this, where we have nitrogen that's singly bonded to 3 hydrogens here, and then has a lone pair on it like that. And that works. That works okay. It works great for not complicated structures. If we look at CH2O, right, carbon has 4 valence electrons, so 1, 2, 3, 4. Each hydrogen has 1. Oxygen has 6, so 1, 2, 3, 4, 5, 6. Right, so if I'm going to draw this connecting the dots method, I'm going to put carbon in the middle. I'm going to connect 2 of these lone pairs to hydrogen, and I'm going to connect 2 of those lone pairs to 2 of those unpaired electrons to oxygen, and I'm going to end up with a structure that looks like this, where I have the 2 hydrogens there, a double bond to an oxygen, and then the 2 lone pairs on the oxygen like that. And this method is fine. It works okay. It gets a little bit more complicated, and we have to think about things like charges. So like when we're drawing structures for ions, an easier way, or another way to think about it, rather than connect the dots, is to look at something like the total number of electrons within the structure. So for example, if I'm looking at something like SO4 2-, so sulfate, the sulfate ion. So here, the first thing I'm going to do is determine the total number of electrons. Each sulfur atom has 6, each oxygen atom has 6, and then the -2 means that I'm going to add 2 electrons to the structure. So I'm going to end up with 6 times 4 is 24, plus 6 is 30, plus 2 is 32. So I have 32 electrons that I need to account for within my structure. Okay, so once I have the number of electrons, I'm going to pick which atom I want to be in the middle. In this case, it's going to be sulfur, because the atom in the middle is typically going to be the one that's less electronegative, unless we're talking about hydrogen. Hydrogen can never be in the middle, because it can only form one bond. But anything else can, and so in this case, sulfur is less electronegative than oxygen, so I'm going to put sulfur in the middle. All right, so sulfur's in the middle. I have 4 oxygens that I need to bind it to, so I'm going to draw 4 bonds to sulfur, with each an oxygen there. Okay, that counts as 2, 4, 6, 8 electrons. So I've removed 8 electrons from my total, which means I still have 24 electrons I need to account for. If I look at my structure, there are some oxygens that don't have an octet. So I'm going to add electrons until everything has an octet and see where that gets me. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've added 24 electrons, so I don't have any left in my pile, but each oxygen has 2, 4, 6, 8 electrons. The sulfur has 2, 4, 6, 8 electrons, so everything has an octet. Everything has the right amount, and my structure contains the right amount of electrons. So I'm going to put it in brackets, put a -2 on the outside because it's an ion, and that's okay, right? And that's a valid structure right there. This is a little bit easier than the connect the dots method for this one, because remember, for sulfur, when we draw the Lewis structure for sulfur itself, it looks like that. It looks like it can only form 2 bonds, but it turns out that sulfur can't only form 2 bonds. It can form 4. And in fact, it can actually form more than that, because it can expand its octet, which we'll get into in a second. So it makes it easier to look at things that don't necessarily follow the whole oxygen makes 2 bonds thing, to do this method instead. And then if I look at another one, so CHOF, right, do this again, determine total number of electrons. Carbon comes with 4, hydrogen comes with 1, oxygen comes with 6, fluorine comes with 7, so that's 13, 14, so I have 18 electrons that I need to account for in my structure. I'm going to pick the one that I need to pick a central atom here. Fluorine's the most electronegative element. Oxygen's highly electronegative. Carbon is slightly more electronegative than hydrogen, but remember, hydrogen can't go in the middle because it can only form one bond. So I'm going to put carbon in the middle. Once carbon is in the middle, all right, I'm going to now say, okay, I need to bond it to a hydrogen. I need to bond it to an oxygen. I need to bond it to a fluorine. Okay, so that uses 6 electrons, which leaves me with 12. Hydrogen's okay because it has an octet. 2, 4, 6, 8, 10, 12. Okay, so that adding lone pairs uses all my electrons, but carbon doesn't have an octet. Remember that fluorine cannot double bond. Oxygen, however, can. So I'm going to make this, instead of this being a lone pair, I'm going to make it a double bond. So my final structure looks like this, where I have carbon, oxygen, double bonded to an oxygen, single bonded to a hydrogen and a fluorine, 2 lone pairs on the oxygen, and 3 lone pairs on the fluorine. I like this method a little bit better simply because it's less kind of confining you to the box of the atomic Lewis structure. Whatever works for you is fine, okay? But what we haven't talked about yet is kind of a way to assess the validity of a Lewis structure. So like how to determine if a Lewis structure that we've drawn that looks like it's okay is okay, or like if there's a better way to draw it. And one of the ways that we use, or one of the things that we need to think about when we're looking at the validity of a Lewis structure, is something called the formal charge. And the formal charge on an atom is essentially, it's going to be based on the number of electrons that I've assigned it within the structure. Let's consider carbon monoxide. So when I look at the structure for carbon monoxide, right, carbon comes with 4 electrons, oxygen comes with 6, which means I have a total of 10 electrons that I need in my structure. Carbon single bonded to an oxygen, that's 2. All right, 2, 4, 6, 8, 10, that doesn't work. What ends up needing to happen for everything to have an octet is that I end up needing a triple bond between the carbon and oxygen. Carbon has a lone pair, oxygen has a lone pair. It's the only way to draw the structure where with 10 electrons, where both of those things get an octet. So, all right, let's look at this for a second. If I look at the total number of electrons that I have assigned to oxygen, and to determine that, what I'm going to do is I'm going to essentially take these bonds and I'm going to split them in half. 1 electron from the bond goes to oxygen, 1 electron from the bond goes to carbon, and then I'm just going to count the number of electrons that are there. Right? So for oxygen, it counts as 1, 2, 3, 4, 5. So I have assigned oxygen in my structure 5 electrons. And I've assigned carbon 1, 2, 3, 4, 5 electrons. So each one is essentially what they're shared, but for the purposes of formal charge, I'm going to split them, right? And I've assigned each one 5 electrons. Well, carbon, we remember, started out with 4 electrons, right? Because it's got a valence of 4, so it started out with 4 electrons. So if I take the number of electrons that we start with, which is 4, and I subtract off the number of electrons that we added, that means that carbon is carrying a 1 minus formal charge. So this carbon has a charge of -1. And if we do the same exercise for oxygen, remember, starts with 6 valence electrons. We've assigned it 5, which means we've taken away 1, which means that oxygen is now carrying a +1 formal charge. Okay, so essentially, to determine the formal charge, what we're doing is we're taking the number of electrons that it started with, and we're subtracting off the number that we assigned. And when we think about the number that we assigned, we remember we're going to count lone pairs as all on that atom, and then we're going to split bonds. Okay, so the total formal charge has to add up to equal whatever the charge is on the molecular ion. In this case, carbon monoxide is neutral, which means that the total formal charge has to add up to be 0, which it does because I have a -1 and a +1, so -1 plus 1 equals 0. That's okay, it works, but it's there and it's something to consider, right? So that carbon isn't neutral, it's not -1, the oxygen is +1, total makes a neutral molecule, okay? If I look at NO3 minus, so I'm looking at the nitrate ion. Here, again, looking at the Lewis structure, nitrogen comes with 5, oxygen comes with 6. I have a negative charge, so 6 times 3 is 18, plus 5 is 23, plus 1 is 24. So I have 24 electrons that I need to account for within my structure. change to a different color because the red's annoying me. Put the nitrogen in the middle. It's less electronegative than oxygen. Single bond here, here, here. What I need to end up doing, so 2, 4, 6, 2, 4, so that uses 6. It's 8, 10, 12, 14, 16, 18, 20, 22. In order to get everything to have an octet, I need that double bond there between the nitrogen and the oxygen. Okay, so let's look at this in terms of formal charge. This oxygen here, the one that has 2 bonds here, I've assigned it 6 electrons, right? The oxygens that have 1 bond, I've assigned 2, 4, 6, 7. So these 2 oxygens here are assigned 7 electrons. And the nitrogen I've assigned 4, which means that this oxygen here is carrying no formal charge. But this oxygen, along with the other one, is carrying a -1 formal charge. And this nitrogen is carrying a +1 formal charge. It started out with 5, it ended up with 4. So that nitrogen is +1. Oxygen is, these 2 oxygens are -1. The oxygen is 0, which adds up to a total of -1, which it needs to match the charge on the ion itself. Okay. All right, so given the fact that we have this idea of formal charge, in order to determine what the best Lewis structure is, we need to take into account formal charge on ions. And essentially, the way to think about this is to minimize the number of ions or atoms within the structure that are carrying a formal charge. So if I look at SO4 2-, the structure that we drew before for sulfate looks like this, where we had the sulfur, it's singly bonded to each oxygen, right? And we had 3 lone pairs on the oxygens. So the structure looked like this. Now, and then we put this in brackets and we said this was 2-. If I look at this structure in terms of from a formal charge perspective, each of these oxygens is carrying a -1 formal charge. And the sulfur is carrying a +2. Remember, sulfur started with 6, and it ends up with 4, which means that it's carrying a +2 formal charge. So is there a better, so every single atom within that structure, in the way that we've drawn it, is carrying a formal charge. Blech. 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 Is there a way that we can draw this where not everything is carrying a formal charge? And it turns out that there is, right? The skeleton is going to remain the same. But remember, we talked about this idea of things that can expand their octets. And it turns out that sulfur is an atom that is an octet exception. It can expand its octet to form up to 6 bonds. And so what happens, a better way to think about this structure is to think about it as having 2 double bonds to oxygen, right? If we do it this way and assign our lone pairs here, now the only thing that's carrying a formal charge are these oxygens here. The sulfur is 0, the oxygens that have double bonds are 0. So again, the total formal charge adds up to B-2, which it needs to be to match the charge on the ion. But in this case, only 2 atoms are carrying a formal charge, as opposed to this one, where 5 atoms are carrying a formal charge. So which one is better? Right? Which one is more representative of the bonding that's present in sulfate? Well, it turns out that neither one of them are great, but this one is better because we're minimizing the amount of formal charge. Right? So when we're looking at the validity of Lewis structures, how do we determine if we've drawn a good Lewis structure? What we're looking for, does everything have an octet? Right? If it's hydrogen, does it have a duet? Does everything else have an octet? We're going to try to minimize formal charge. So minimize the number of atoms that are carrying a formal charge. And we're going to put the more negative formal charge on the more electronegative elements and the positive formal charges on less electronegative elements. It's just going to make it easier and more stable. Okay. For organic compounds, this turns out to be relatively straightforward for determining what's got a formal charge. Because if I look at carbon, right, carbon forms 4 bonds. If you look at your structure and your structure doesn't have 4 bonds to carbon, it's carrying a formal charge. If oxygen or nitrogen forms 3. If your structure has nitrogen with something other than 3 bonds, it's carrying a formal charge. Again, oxygen forms 2, carrying a formal charge if it's got less or more than 2. And halogens form 1. So if they've got more than one, they're carrying a formal charge. All right. We'll go over this in more detail when we look at more complicated organic structures and when we start to look at, okay, I can arrange this in a number of ways. How do I tell which one is the best? But for now, take a look at there's some review practice, some practice with drawing basic Lewis structures, both on the handout that I gave you in class, as well as on Canvas. Check it out. Make sure you feel comfortable with these Lewis structures. If you don't, please come and ask questions, and I will see you in class.